Happy Friday, everyone. So we are caught up in the curriculum and where we should be. And so I thought today I'd do some problems from like Riemann sums. We'll do the you-do problems from yesterday. And then I'm going to give you a preview into the Fundamental Theorem of Calculus Part 1. Just as a reminder, there is a paper homework due Monday. So there is a homework due Monday by midnight. I have a Zoom meeting today at our normal time and Monday at the normal time. Again, I put that on the announcements, 3:30 to 4. There is a password. Look for that in the announcements. It's going to be the same password every single time, so you don't have to look it up every time once you know it. But yeah, so we're going to start with some problems. And so actually, let's do the old you-do. The old you-do. So if we look at this guy, so that was the x cubed plus 3x minus 4 all over x squared dx. Okay, so before you can take the antiderivative with what we understand, we want to rewrite this. And so we can split this up as x cubed over x squared plus 3x over x squared minus 4 over x squared, all dx, which is equal to the integral of x plus 3 over x minus 4x to the negative 2 dx. Okay, so at this point, we can split it up. And so this is going to be equal to the integral of x dx plus 3 times the integral of 1 over x dx minus 4 times the integral of x to the negative 2 dx, which is 1/2 x squared plus 3 natural log of x minus, plus 4x to the negative 1. Oh, sorry, I keep doing this dx thing and I don't want to do it. Plus c. Don't forget the plus c. Never forget the plus c. There will be points off if you're doing a indefinite integral and you forget the plus c. Let's do the other you-do. So this guy was the integral of 8x minus 4e to the 5 minus 2x dx. So we want to rewrite this. So we can split it. So this is the integral of 8x dx minus 4 times the integral of e to the 5 minus 2x dx. With what we understand so far, we don't necessarily know how to deal with something that's a little bit more complicated in the exponent. We will when we get to u substitution. So u substitution will be how we handle this in the future. But today, substitution. We don't have that tool if we have never taken calculus before. So instead, what we're going to do is we're going to rewrite this. We can split this across that minus sign. And so this will be equal to... Oh, I meant to pull that 8 out in the front. But anyway, so this guy, that antiderivative is going to be 4x squared. And then minus 4 times the integral of e to the 5th times e to the negative 2x dx. All right? And then what I want you to notice is that e to the 5th is a constant. It's a number raised to a power, which means that this is a number. So we can pull that out. And so this is 4x squared minus 4e to the 5th times the integral of e to the negative 2x dx. And then we can use what we know about e to the kx and take the antiderivative to be 4x squared minus 4e to the 5th times 1 over negative 2 e to the negative 2x plus c, which cleans up to be 4x squared minus plus 2 e to the 5th e to the negative 2x all plus c. So I just multiplied these guys. And in fact, we could combine these back into something of this form if we wanted to, but I'm just going to leave that alone. All right, the next kind of problem we're going to look at is reverse engineering a Riemann sum, specifically the limit definition of a Riemann sum. Again, if we were to just like, if you were to cover that limit as n approaches infinity, and I'm doing that with my hand, but you can't see it, and just look at the Riemann sum part, you could do the same thing for an approximation. But today, we're going to rewrite this Riemann sum definition of an integral as the more classic way of writing the integral. And so to do this, you want to start by identifying your width. So the width of each rectangle. So there are n rectangles. So you ignore that limit and we just look at the number at the top here. And so if we're looking at this, we want to identify what represents the width. Now this is our width. It's always going to be something over n, and it's either going to be inside the sum, but it could be written outside the sum as well. It will always be after the limit, but you are looking for the width. And so if we see that, then delta x is equal to 1 over n. So the interval is that top number. So here it's 1, and so the interval is 1 wide. Therefore, when we look at our limits of integration, they should be 1 apart. Now, if this was a 3 above the n, then these would be 3 apart. The next thing that we want to identify is what we're plugging in for x. And so if you're looking at this, you always look for something with a j in it. And so here we find our j. And if you notice, it's the width of a rectangle times j, and it's simplified, and then it's being added to a number inside some parentheses. That number is your starting limit. If you have this piece missing, you're starting at 0. So here it's 1 plus j over n. So your first limit of integration is 1. So first limit of integration is 1. Which means, since the interval is 1 wide, that the second limit of integration is 2. All right? And the second limit of integration is 2. And then the next thing you want to look at is where are all the places that you see that number plus j times something over n? This is your x value. And so let me get a different color going on here. Let's say, so this piece right here is x. So anywhere you see that 1 plus j over n, it will be an x. Or for a different problem, it'll look a little bit different. A lot of the problems you'll see, there's only one place, but let's say that it happened twice. Then you would just replace both times with x. So anyway, that means that our function is 7x plus 4. Okay, so this is how you reverse engineer these Riemann integration. Now, if you can do this, then you can use shortcuts for solving these boys, okay? So right now, what you have are those power sums. And it's good to be able to do that at least a few times in calculus, but it's an even more useful skill to write it in this form. Because in this form, what we can do is we can graph this and find the area under this curve. And then, starting Monday, when we learn the Fundamental Theorem of Calculus, you can use the Fundamental Theorem of Calculus to solve this, which is way, way easier than doing the Riemann sum, power sum version of this. But to solve this, let's draw this real quick. And so we've got ourselves a line going up, and we're starting at 1 to 2. And we're looking at this shape right here. Now, we can split this up into a rectangle and a triangle. So at 1, the height is at 7 times 1 plus 4, which is 11. So I'm just typing that, or not typing that, I'm just plugging that into my function. And then at 2, it's at 7 times 2 plus 4, which is 18. Okay, so that makes it easier. So then this is a 1 by 11 rectangle, which is 11. And this guy is a triangle, so that's 1/2. The base is 1, and then the height is going to be 18 minus 11, which is 7, and so you get 7/2. And so your answer to this guy up here, which is this sum, will be 11 plus 7/2, which is equal to 14.5. And again, by just redrawing it and thinking about it as the area under the curve, solving it just takes less time. So I really recommend get familiar with solving this type of problem. So let's go on and let's do another problem like this. So let's solve this puppy. So again, if you're looking at this, you'll notice that we have in rectangles. And each rectangle, if we're observing this, we want to find what is our width of our rectangle. And so the only option we have is actually outside the sum, and that's going to be 3 over n. Which means the width of the interval is 3. So your limits of integration will be 3 apart. Now, when we're looking up here, our next step is to identify what our first limit of integration is. So we're looking for something of the form blah plus 3j over n, because you're adding j widths to your initial value, to your first limit of integration. And so for us, we see that this is -3. And so we can put that -3 there. And then 3 more, because our interval is 3 wide, is going to be at 0. So our limits of integration are from -3 to 0. And the thing that looks like that blah plus 3j over n is our x, which means our function is 9 minus x squared under a square root. Now, at this point, we don't know how to handle this. It will end up being something like u substitution or integration by parts when we go through this later, and some of that's in Calc 2, which hopefully will be in class for you guys. But we can look at this as an area. Now, I think there was a problem like this on your WebAssign, and so if you were like confused, like how do I handle this? What shape is this? This is a semicircle. This is the top of a circle with radius. So this is a semicircle, center at 0, and radius of 3. Radius of 3. So if you've forgotten like the form for like a circle or whatever, maybe go and review that a little bit. Yeah, but otherwise, like this is what you got. And so when we draw this graph of the semicircle, we're going to start at -3, it ends at 3, and we go up. Imagine this is perfect, and its height is at 3. And we're looking for the area of this part right here. So we're going from -3 to 0. Bum-ba-dum. And so that's going to be a quarter of a circle. So that's 1/4 times pi r squared, and our r is 3. So that is 9/4 pi. And so our ultimate answer to this is 9 pi over 4 is our answer, which is kind of cool that we were able to do that so easily by just being able to recognize, number one, what this is asking us to solve, writing it in this form, knowing that this is asking what's the area under this curve from this value to this value, drawing it, and then using some geometry to solve. So it's pretty cool that we can do that. So we're going to do the cliff notes of the Fundamental Theorem of Calculus. Again, we'll do a longer series of this on Monday, but if you're just using it, it's very straightforward. We'll understand why it works next week, but right now, suppose that capital F prime is equal to little f. That is, capital F is an antiderivative of little f. So little f is the derivative, capital F is the antiderivative. Then, if you're taking an integral, a definite integral from a to b of f of x, little f of x dx, then that is going to be equal to capital F of b minus capital F of a. So this is the Fundamental Theorem of Calculus, part 1. But let's just see this in practicality. So if we're going from -4 to 7 of, let's just do 3x squared plus 1 dx, then we just need to find an antiderivative of 3x squared plus 1. So for a definite integral, you don't have to worry about a c, because you just need one antiderivative, so you might as well let the c be 0. And so the antiderivative is going to be x cubed plus x. All right, so that's our antiderivative. And then you do this bar to mark that you're not done, from -4 to 7. So that's going to be 7 cubed plus 7 minus -4 cubed plus -4 to solve this, which is equal to 418. So again, this is way easier than doing the Riemann approximation of this deal. And so when you are doing these power sums from here on out, you can check some of them with the Fundamental Theorem of Calculus. So let's go on and let's do kind of like what we were doing before, where we rewrite a Riemann sum as the definite integral, and then we're going to work through a power sum because I think it'd just be good for you to get an example of that. And then we'll just show it with the Fundamental Theorem of Calculus to know what our answer should be. So let's rewrite this guy. And so if we're looking at this, again, there are n rectangles. Where the width of each rectangle is 2 over n. So if we're looking at the example, there are n rectangles with the width of each rectangle being 2 over n. So we're looking at this guy, which means that our interval is 2 wide. So our limits of integration are going to be 2 apart. They're going to be 2 apart. So what we want to discover is, what is our first limit of integration? And so we look for a blank plus 2 over nj. So we see this 2 over jn, and they appear twice. But what you'll notice is there's not something like 1 plus or -3 plus. What that means is that the first limit of integration, so it starts at 0, because you're doing 0 plus. And so this is 0, And since the interval is too wide, that means this goes to 2. So we're going from 0 to 2. Actually, let's undo that and let's write that again. So 0 to 2. And then of what function? So we look at this and we're like, okay, so we see this 2j over n appearing twice. And so we have squared and we've got cubed. And so these are our x values. So x and x. So our function is going to be x squared minus 8x cubed. All right, and then from what we learned about the fundamental theorem of calculus, we can find this value very, very quickly. And so let's solve it. So from 0 to 2 of x squared minus 8x cubed dx, we're going to take that antiderivative, so it's going to be 1/3 x cubed minus, and then it becomes x to the 4th, and then 8 over 4, which is 2. So this is our antiderivative from 0 to 2. So we can plug these in. So we get 1/3 2 cubed minus 2 times 2 to the 4th, all minus 1/3 0 cubed minus 2 times 0 to the 4th. And we end up with 8/3 minus 32, which is negative 88/3. So let's do this problem with power sums. And so we're going to start with rewriting this and clearing this up. So we're going to get the limit as n goes to infinity of 2 over n times the sum from j equals 1 to n. And then if we square this 2j over n, you're going to end up with 4j squared over n squared minus, and then 8 times this cube. So 8 times 2 cubed will be 2 times 2 is 4. Oh, duh. Okay, so it's 64 j cubed over n cubed. All right. And then we're going to split this up. So the limit as n goes to infinity of 2 over n times, and we're going to pull out that 4 over n squared from j equals 1 to n of j squared minus, and we're going to pull out 64 over n cubed from j equals 1 to n of j cubed. So we can use those power sums, and we get the limit as n goes to infinity of 2 over n times 4 over n squared. And then the power sum from j equals 1 to n of j squared is 2n cubed plus 3n squared plus n all over 6. And then minus that 64 over n cubed. And the power sum of j cubed is n to the 4th plus 2n cubed plus n squared all over 4. All right, and then we're going to distribute this whole thing. So we've got the limit as n goes to infinity of, and you know what, I'm going to press pause and do this off screen. So when you distribute this, you end up with this. And so if we look, we've got only 2 where the powers are the same. Everything else, you have at the bottom, the denominator has a higher power of n than the numerator. So it's n cubed is underneath n squared, n cubed under n to the 4th under n cubed, n to the 4th under n squared, which means that all of these, as n gets really, really big, your denominator is growing much, much larger than your numerator. So this is going to 0, this is going to 0, this is going to 0, and this is going to 0. And so the only thing left when you let n go to infinity, n cubed over n cubed is 1, and n to the 4th over n to the 4th is also 1. So you end up with 16 over 6 minus 128 over 4. Which, when you simplify this, is 8/3 minus 32, which we already know is, I think it was negative 88/3. I'm not sure. Let's go back. Oh, yep, negative 88/3. You could do that. Yeah, So we could do it the long way with a power sum, or you can go through and do it the shorter way with the Fundamental Theorem of Calculus. But just overall, this is just good practice. And so for today, your you-do problems, I'm going to give you a couple like this, where you use that Riemann sum to solve. So let's do this guy. So the limit as n goes to infinity of the sum from j equals 1 to n of 5 over n times the square root of negative 3 plus 5j over n minus, or plus, let's do plus 3 minus 5j over n. So I want you guys to try to do this guy. Actually, oh, no, wait. All right, I didn't like that one. And so it would be kind of really hard to do. And so let's do this guy. So minus 3 plus 5j over n squared plus 6 minus 10j over n. All right, so this is going to be a little bit of a challenge. My recommendation is rewrite this piece to match this piece before you begin. But I recommend do this with the Fundamental Theorem of Calculus. So use those antiderivatives, and then also do it with power sums. It's just good practice. Get in there, get a little bit done, and before you even begin, rewrite it as this guy, just so that you know what your definite integral is that you're solving. But I think that's it for the day. So Zoom today at 3:30. Have a wonderful weekend. Bye.